Hello, welcome to Econometrics Melody. In this video, we'll discuss about the normal distribution. Normal distribution is also called as the Gaussian distribution or the bell curve distribution. Let us start off with the basics, some of the basics before we delve deeper into the normal distribution. And by the help of the graphs or the plot, we want to introduce how the normal distribution is created. So this is the combination of 6 graphs. Each graph contains the plotting of the first and the second. The second one is simply the reflection on the x-axis because the value of y is negative in the second case. First one, x squared, is it gives us a parabola, and we want to introduce how the bell curve originates. And the second one is 1 by 2 to the power x squared. For the positive value, we get this kind of graph, and 0.5 to the power x squared. 0.5 is equals to 1 by 2, otherwise 2 to the power minus 1. So 2 to the power minus x squared, that is why is the index is negative. 2 to the power minus x squared, that is why we get a bell curve. And in the next case, we have the index negative in itself, that is why we see some sort of bell curve. In the another one, we have the base is 1.2 and its index is again negative, that is why we get a bell curve. And in the last sixth one, we have 0.5, that is 1 by 2 or 2 to the power minus 1, and the 2 to the power minus 1, and this term when multiplied it becomes positive 2 to the power x squared, that is why we get this curve. So in order to get the bell curve, we must have the base greater than or equal to 1 and its index must be negative. And the power should be here negative x squared. The variable should have power in its square term. And let us say the exp, it is the Euler number, and the Euler number to the power minus x squared is going to give us a bell curve. And before that, let us see what is the graph of e to the power x like. It is increasing function, and e to the power minus x, if we remember our exponential distribution, we had 1 by b into e to the power minus x by b. It was this kind of graph. And a Laplace distribution, also called as the double exponential distribution, was the combination of this and its reflection on the y-axis. So we can say that e to the power minus x squared gives us a bell curve, and we'll work on this in order to derive our normal distribution in our next part. And let us see a program called norm. This is a program written by Econometrics Melody, and we want to see how do we derive the normal distribution. So e to the power minus x squared, Euler number e, and the index is negative x squared. X is our variable, and we get this curve, bell-shaped curve. And e to the when to this variable x, if we subtract something, then it is going to act as the mean, or it will help, or it is called as the location parameter, and it will help us shift the location by this unit. Similarly, if we divide this our variable by certain values, then it will help us increase the variance, increase its, so this is called as a scale parameter. And here the mean or shift parameter is 0, that is why they are centered at the mean or 0. Similarly, if we multiply it by 1 by root 2, or in other words, if we divide it by root 2, then the height of the bell curve will be scaled down. And further, if we divide it by 1 by root 2 pi, so root 2 pi, this will help us derive the normal distribution, and its area will be preserved to 1. Now let us see the formula of the normal distribution in another section, and let us compare the graph. There are two graphs representing the normal distribution. On the right hand side, we drew this graph by making use of normal den. This is the Stata function to draw the normal density PDF, and this is its generic formula: 1 by d, where d is the standard deviation, 1 by d into root 2 pi. So this is going to help us scale down or preserve the area of the normal distribution to 1, and 1 by 2 x minus mu divided by d, where mu is our location parameter or the mean of the distribution, d is our scale parameter or the standard deviation, and a square. So in either of the cases, we get the same graph, normal distribution. Now let us say the formulae of the normal distribution and explain them as well as derive them. So some of the formulae of the normal distribution, we need to calculate the CDF and PDF for hypothesis testing as well. And the mean of the normal distribution is mu, this parameter, location parameter mu, and the variance of the normal distribution is d square, sigma square. We calculate the PDF of normal distribution making use of this formula, 1 by sigma into square root of 2 pi, and Euler number e to the power minus 1 by 2 x minus mu divided by d. X minus mu divided by d, this sigma, this is called is the z score. X minus, this is a location parameter divided by the scale parameter. And then to calculate the CDF of a normal distribution, we use 1 by 2 into 1 plus ERF. This is the error function for this, and this entire term is acting as a variable. That is again z score, x minus mu divided by d, and square root of 2. So z score divided by root 2. ERF is the error function, and ERF of x is going, we calculate the ERF of x by integrating 0 to this x. Here x is everything inside this bracket, so that is x minus mu divided by sigma root 2 e to the power minus t square, and we integrate with respect to dt and multiply it by this term 2 divided by root pi. We'll also calculate it and we'll show it. An error function of x, this is really the probability of random variable with a normal distribution having mean 0 and the variance 0.5, that lies in between minus x and x. Now let us calculate the CDF of normal distribution. First of all, a graphical depiction. So this is the CDF of our normal distribution centered at 0. Normal, this is the Stata function to calculate the CDF of a normal distribution. The value of, for the value 1, standard deviation 1, and let us see what does it look like. It is 84%, and this is the generic formula to calculate the CDF. 1 by 2, that is 0.5, and 1 plus, this is the ERF function. So ERF, for ERF we take x minus m divided by d root 2. So let us see, we have used the Mata Quadrature class of the Mata in Stata, and let us calculate how did we get this ERF to be 0.68 for the value of x to be 1, and we'll show it. First of all, let us say both of them should yield the same result. Now we want to see how did we get this 0.68. So the quadrature class, it is supported only from Stata 16 onwards, I guess. So I am going to demonstrate it on Stata 17. We will have another video to explain the quadrature class, to derive the integration using the quadrature class. In some, we'll explain it in details in some other videos. So let us see it. We have set the limit of x minus m, it is the standard normal distribution, divided by d is 1 and square root 2, and this is our ERF function, 2 divided by square root of pi and e to the power minus x square. And let us run it for the value of x to be 1, and what is the value that we are going to get, and it is this value 68.2869. for the value of x is 68.69. And let us also derive it for the another value for the x is equals to 2 and 3. This will be useful for our, for x is equals to 2, it is 95%. And let us run it once again for the value of x to be 3, and let us see what is the value like. So for the value of x is equals to 3, it is 99.7309. So let us copy the ERF that we have calculated here, and so 0.682869, the first value for the value of x is equals to 1. So let us run both of them. They should yield the same result, one by the Stata function and the second it's generic in its generic form. And let us check it by this example. It should be 84, nearly 84%, less than 1, it should be 84%, and that is what we get over here. This represents the CDF, cumulative distributive function, and age ERF minus x is equals to ER of x. Similarly, for the value of -1, z score -1, we can use the ERFF +1, but with minus over here. And let us see what is the CDF like. In both of the cases, it should be equal. It is nearly 16%. And let us check it by the help of this graph. Less than 1, it is 16%. Less than 1, it is 16%. And what is the area included between +1 and -1? Another program will help us depict it. So the area included between plus and -1, it is nearly 68.27%. Now let us calculate the CDF for the Z score to be 2, and for the value of 2, ERF was equals to 0.95449, this value, and both of them should now yield the same result. It is 97.72%. And let us see what is the value for 2 less than 2. Less than 2, it is 97.72%. This is again the CDF. Now let us calculate the CDF for Z to be -2 or less than -2. In both of the cases, we get the same result. It is nearly 2%. And let us see our CDF graph. Actually, it is a PDF graph, but this term, so less than the 2, it is 2.28%. And what is the area included between plus and -2? It is 95.45%. Now let us calculate the CDF for the Z score to be 3, and let us see both of them. So for the value of 3, the ERF function, it should yield 99.9973, so 0.9973 this, and both of them should yield the same result. The Stata function as well as its generic form, we see 99.86510, and let us see it by the help of graph as well. For less than 3, it is 99.87, and let us see for J to be -3. So what is less than -3? What is the CDF for Z score to be less than -3? The value is nearly 0.13%. And let us see by the help of graph as well, 0.13%. And let us see the area included between plus and -3. Plus and -3, it is 99.73%. It is almost 100%. That is why we call it as 6 sigma plus 3 sigmas towards the right and -3 sigmas towards the left. So this 6 sigma is covering almost all the area of this distribution, normal distribution. Now let us see about the PDF of the normal distribution. First of all, this program is going to display the normal distribution. So this is the PDF of a normal distribution. Standard normal distribution is centered 80 because its mean is 0 and its variance is 1. Similarly, let us say what is the area. Standard normal distribution is symmetric. So at this mean value, the mean value for this standard normal distribution, the mean is 0 and the variance is 1. So this normal distribution, the PDF of the normal distribution, less than 0, it covers 50% of the area, and greater than 0, it covers 50% of the area. It is symmetric. Now let us try to calculate the PDF of a normal distribution. Normal den, this is the Stata function to calculate the normal distribution, PDF of a normal distribution for X, and the mean value and its standard deviation. And this is our generic formula: 1 divided by standard deviation into square root of 2 pi into e to the power -1/2 x minus m divided by standard deviation sigma and its square. Both of them should yield the same result. It is 24%, and both of them they give the same result. And here we are going to calculate the probability for x to be 3 and the mean value to be 5 and standard deviation is 2, and this is its generic formula: 1 divided by standard deviation 2 and square root 2 pi into e to the power -1/2 x minus m. X is 3, m is mean is 5 divided by 2 is our standard deviation, and it's a square. Again, both of them should yield the same result, and we have seen it to be 12%. Now let us explore some other properties of the normal distribution, and we are going to plot the graph of different mean but same variance, and let us see what does it have to offer. So there are three normal distributions with a different mean. Mean is the variable over here, mean is changing, and standard deviation. Both of them have the standard deviation to be 1, the variance to be 1, and the first one, it has the mean of -5, the second one is the mean of 0, and the third one, its mean is 5. So the mean or the location parameter simply helps us shift the graph. Another graph, we have same mean but different variance. Let us see, all of them should be centered at the mean. Here we have taken the mean to be 0, but with different variance. For the first one, the variance is 1, the second one 2, and the third one is 3. So this program will give us the normal distribution for different mean and different variances, and let us see. So the distribution, they are the normal distribution. The first one has the mean of -4 but the variance of 1. The second one has the mean of -1 but the variance of 2, and the third one has the mean of 2 and the variance of 3. By shifting the mean, simulating the mean, we are going to see the graph of the normal distribution with the mean from 1 and ranging it to 9, increasing all the way to 9, and this will simply shift the graph by the same unit. The mean is also called as the location parameter. This will simply help us shift the graph by the given units. Now let us reinforce this concept, but this time we are increasing the mean or the location parameter from 20 all the way to 30. And now let us simulate its scale parameter or the variance. We are going to increase the variance from 1 to 6, and let us see. This time let us change the variance from 9 to 18. Now let us say this function less, the program that we have written, the program called less, this will give the area for the less than this parameter, and we will use this in order to test the one-tail hypothesis in our other video. So less than 0, we get the area, they are symmetric, 50%. Less than 0 is 50%, so the greater than 0 is again 50%. Less than -3, we get a value, it's a 0.13%. we have seen it already. And less than 3, it is 1 minus less than -3, so it is 99.87%. Less than -2, we get this value. Less than -2, it is 2.28%, and greater than 2 should also be equal to the same value. Less than 2, we got less than -2, we got 2.28%. So greater than 2, it should also be 2.28%. So greater than 2, it is again 2.28%. They are symmetric. Less than -1, let us see what is the area. Less than -1, it is 15.87%. So greater than 1, it should also be 15.87%. Normal distribution, it is a symmetric distribution. Greater than 1, we got it at 15.87%. We'll use this program in order to test the one-tail hypothesis. Less than 0.5, let us see what is the value of less than 0.5. It is 69.15%, and greater than -0.5 should also be of the same value. Now let us see another program that we have written. It is called as the area graph. This we will use it to calculate, to test the two-tail hypothesis in our other video. So the area between plus and minus 1.96, this is score, Z score 1.96, -1.96 and plus 1.96. It covers 95% of the area, and that is why we are left with 2.5% each on the either side. And this will give us the area between 1.96 and for the Z score -1.96 and plus 1.96. Again, this is the same graph. And what is the area between plus -1? Z score is plus -1, it is 68.27%. We'll use this program to perform the two-tail test. Similarly, we can manipulate the significance level. And let us see, the significance level is 1. So significance level 1, so this is divided into two parts, 0.5 and 0.5 on the each side. Similarly, we can increase the significance level to 10, that is 10%, so 5% on the left and 5% on the right, 5% of the area on the left and 5% of the area on the right. Similarly, for the Z score 0.5 and significance level 10, the graph looks like this. Similarly, we have written a program to perform our Z test, and we have named it our Z test. And for the value of n to be the sample 120, its mean is 10 and its variance is 5, or the standard deviation is 5, and we want to test the hypothesis whether the mean is 11, and we will see it in our another video, just a graphical depiction. And based on this result, we will make our two-tailed test. For the sample 300, the mean is 27 and its standard deviation is 10, and we want to test the hypothesis whether it is the mean is 30. And again, we will use it in our video, another video. So this is what graph look like. Sometimes the histogram may indicate for the normal distribution. If the histogram of our data indicate that they are normally distributed, then we can perform the test related with normal distribution. Now let us see some of the uses of the normal distribution. I have collected from different sources. Normal distribution is commonly used probability distribution in statistics and data analysis. It is also used in modeling the distribution of continuous data, such as measurements of physical or biological processes. It is used in statistical inferences, such as estimating the mean and standard deviation of the population from a sample. It is also used in comparing the groups of data using statistical tests such as t-tests and ANOVA. It is used in many real applications such as quality control, weather forecast, stock market analysis, economics, and many other fields. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.